All right, guys, welcome to a brand new module. And in this module, we're going to tackle the topic of authentication. And it's something that is often thought of as incredibly complicated, but it doesn't have to be. And we're going to take it step by step from beginning to end so that you get an overview of the entire process of setting up authentication from scratch. So, why do we need to authenticate? Well, as we're creating our website or web app for users to use, then these users are going to start generating data in the website. They might like certain posts, they might interact with other users, there might be messages created or recipes created. There's always going to be some user data created. And in order to associate those pieces of data with individual users, we need to create an account for each user. So they would sign up to our website using a username and a password, and we would essentially create kind of like an ID card for them to uniquely identify them on our database and to save all of the data that they generate onto that account. So the next time that they come back onto the website, they'll be able to use their username and password and log in to our website and be able to access all of those possibly private pieces of information. So this way you don't end up with everybody being able to see, what private messages you're sending around on Facebook or see your direct messages on Twitter. So that's pretty simple. Now, the other reason why you might want to add authentication to your website is to restrict access to certain areas of the website depending on the status of the user. So, for example, if you were Spotify or Netflix and you charge a subscription for accessing certain parts of the website, then once the user pays, you have to update their account in your database to say that they have paid and they'll be allowed to access the TV shows or songs that they're entitled to. So those are some of the reasons why you might want to add authentication to your website. But authentication can be done in a number of ways. Creating a website where we sign up and log in users seems simple enough. But the difficult part of authentication comes from how secure you're going to make your website. So we're going to learn how to progress from essentially a website that's basically secured with a Cheeto to something that is a lot more serious and more consistent with industry standards of good security on a website. So the structure of our website is really, really simple. It has a home page, which has two buttons that allows you to either go towards register or go towards login. And once the user has been registered or logged in and they have been authenticated, then they are able to access the secrets page. So I've kept the remainder of the website pretty simple because we're going to be focusing on a pretty complex topic. So I've created some starting files for you to download so that we can focus our efforts on learning authentication and not get distracted by things like Bootstrap and styling. So once you're ready, head over to the next lesson and download the starting files. And then we're going to get started with authentication. So I'll see you there. All right, so we've taken a look at level 1 encryption, which is basically just storing the password as plain text in our database. So maybe it'll be a little bit difficult for people to get access to our server and access our database. At least you can't just simply right click on a website to view page source and be able to see it in the HTML. At least it's stored at server level. But that's not really good enough. So let's go ahead and see what we can do to improve the security for our users on our website. So let's increase to level 2 authentication. And level 2 authentication involves the use of encryption. So what exactly is encryption? Well, basically, all it is just scrambling something so that people can't tell what the original was unless they were in on the secret and they knew how to unscramble it. This is exactly the same as if you and your friend were sending each other secret messages and you had a key to encode the message that you both knew so that you could decode the message. Now, on a bigger scale, if you've ever watched The Imitation Game or read about the Enigma machine, well, that is basically a form of encryption. And the Enigma machine, if you don't know, is just simply a machine that was used during World War II. When the Germans would send each other messages, they would use the machine to encrypt those messages so that when the messages are intercepted, say over the radio, unless you had the same Enigma machine and you knew what the decoding key was or what the settings were for the machine, then you wouldn't be able to tell what it is that they were trying to communicate with each other. If you're interested, I really recommend watching 2 videos that were done by Numberphile on YouTube. And I've linked to it in the course resources list, but it explains the Enigma machine and it talks about the flaw in the Enigma machine that led Alan Turing and other people at Bletchley Park to be able to crack the code and create what was very much a specialized computer to be able to decode those messages and helped the Allies win the war. And if you ever visit London, be sure to go and check out Bletchley Park, and they have a computer museum next to it as well, which is super fascinating. Anyways, I digress. So back to ciphers and encryption. One of the earliest ways of encrypting messages that we know about is the Caesar cipher. And this comes from Julius Caesar, who was one of the generals in the Roman Empire. And what he did is he would send messages to his generals and he would encrypt it. So if his messenger got murdered along the way, then his messages would be kept secret. And this is one of the simplest forms of encryption we know about. And it's very simple. Let's say we have the alphabet, right? A, B, C, D, E, F, G. All that the Caesar cipher does, it's a letter substitution cipher. And the key for the cipher is the number of letters that you would shift by. So if you knew what the shift pattern was, then you could really quickly decipher the message. So if we were to encrypt the word hello, there's a really neat tool online that can help us do that. It's called crypty.com and it's got 2 I's at the end. And you can basically choose the kind of cipher or encryption that you want to use. And then you can specify the shift. And we're going to say a shift of 3, let's say. So if my text was hello, then it becomes shifted into core. And to an unknowing person and a non-cryptographer, it can be quite difficult to see at a glance what exactly this is trying to say. Now, in modern days and with modern cryptography, this is overly simplistic and it's very, very easy to crack. But there are other forms of encryption which are a little bit more complicated and it involves a lot more maths to make it more time consuming for somebody to crack. But essentially, all encryption works exactly the same way. You have a way of scrambling your message and it requires a key to be able to unscramble that message. All right, so now it's time to level up to the next level of security. And in this lesson, we're going to cover something called hashing. Now, previously, we've already looked at encryption. So taking the user's password and securing it using an encryption key, and then using a particular cipher method, be it a Caesar cipher or the Enigma cipher. No matter which way we chose, we always had a password, a key, and we ended up with some ciphertext, which will make it hard for people to be able to immediately guess what our user's password is. So for example, if we took a password like QWERTY and we used the Caesar cipher method and we decided to shift it by 1, then our encryption key is the number 1. And that creates the ciphertext where every single letter is shifted up by 1. Now, in order to decrypt this, all you have to do, as long as you know what the key is, then you can simply shift all of the ciphertext down by 1 and you end up with the original password. Now, the Caesar cipher is a very, very weak encryption method. It's incredibly easy to figure out what the original text was, even if you didn't have a key. And just to illustrate what bad things can happen when you have a weak encryption system, I'm going to tell you a story from history that tells us why we should not be using a weak encryption system. So back in the 1500s, on this island that we now call the United Kingdom, there used to be two large areas. One was Scotland and the other was England. And they were ruled over by two queens. Scotland was ruled by Mary Queen of Scots, who was a Catholic, and England was ruled over by Queen Elizabeth I. Now, these two ladies between them controlled the land that we now call the UK, but they each wanted to have more power and more land. So, what did they do? Well, Mary Queen of Scots, who ruled over Scotland, decided to plot with her friend Lord Babington to try and assassinate Queen Elizabeth. That way, she would be the legitimate heir to both the English and Scottish throne, and it was kind of a Game of Thrones kind of situation going on back then. But in order to mobilize their forces or try to come up with some sort of secret plan, they decided to send letters to each other using ciphertext. So they came up with a system to encrypt their letters to each other, such that if it fell into the wrong hands, the subject of the letter wouldn't be revealed and they wouldn't end up being tried for treason. But the problem was that the encryption method that they used, which was a letter substitution method similar to the Caesar cipher, was a very weak form of encryption. And Queen Elizabeth had a chief decoder who ended up deciphering their letters and figuring out what their encryption key was. So he decided to take this encryption key and write a letter back to Lord Babington to try and get him to reveal all of the co-conspirators. And what was the end result of having their weak encryption system? Well, Queen Elizabeth decided to accuse Mary Queen of Scots of treason, and hence she ended up having her head chopped off. So this is not what you want to happen to you or your website. So weak encryption systems can end up putting user passwords at risk, and your company might end up metaphorically decapitated, such as in the case of companies like TalkTalk or Equifax, where they ended up getting hacked and lost a lot of the trust of their users. Now, if you're interested in more stories like this and to learn more about cryptography and encryption, there's a really great book recommendation that I would make called The Code Book by Simon Singh. It contains stories like the one that I just told you and more. So if you're interested in this, go ahead and read more about it. Now, how can we make our password more secure? Now, at the moment, the biggest flaw in our authentication method is the fact that we need an encryption key to encrypt our passwords and decrypt our passwords. And chances are that if somebody is motivated enough to spend time and hack into your database, then it's probably not that difficult for them to also be able to get your encryption key, even if you've saved it in an environment variable or somewhere secure on your server. So how can we address this weakest link, the need for that encryption key? Well, here is where hashing comes into play. Whereas previously with encryption, we needed that encryption key, hashing takes it away and no longer requires the need for an encryption key. Well, then you might ask, well, if we don't have an encryption key, how can we decrypt our password back into plain text? Well, the secret is you don't. Let's say a user registers on our website and they enter a password to register with. We use something called a hash function to turn that password into a hash, and we store that hash in our database. Now, the problem is that hash functions are mathematical equations that are designed to make it almost impossible to go backwards. So it's almost impossible to turn a hash back into a password. How is this possible, you might ask? How is it possible that you can turn a password into a hash very quickly and easily, but make it almost impossible to turn that hash back into a password? Well, here's a question. Let me ask you, what are the factors of 377 other than 1 and 377? So basically I'm saying 377 is not a prime number. Not only can you divide 377 by 1 and 377, but there's also two other numbers that you can divide it by. Now, it's your job to figure out what those numbers are. So what might you do? Well, you might divide it by 2. Okay, so that becomes 188.5. That's not a whole number, so 2 is not a factor. What if you divide it by 3? Well, that becomes 113.3 recurring, which is also not a whole number, so 3 is not a factor either. And you might go through this process for a long time, tediously, going through number by number. Well, then you might arrive at the point where you divide 377 by 13 and you end up with 29. So 13 and 29 are the answers to this question. They are the only factors of 377 other than 1 and 377. And as you can see, that process of getting to this point, of finding those two factors, took us a while, right? It wasn't that easy. But consider if I asked you a different question. If I said to you, can you multiply 13 by 29? Well, you would be able to do that really quickly and easily. It would take you almost no time at all to figure out that the answer is 377. So here is a very, very simplified version of a hash function. So going forward, multiplying 13 by 29 is really quick and easy. But going backwards, trying to get back those numbers 13 and 29, starting from 377, is very, very time consuming. So this is essentially how a hash function works. Just add a little bit more complexity and you end up with a real hash function. So they're designed to be calculated very quickly going forwards, but almost impossible to go backwards. And by almost impossible, I simply mean that using current levels of computing power, it would take far too long to make it worthwhile for the hacker. So let's say that to calculate the hash going forwards, it takes a millisecond, but to go backwards, it takes 2 years, then that hacker probably has better things to do with his time. So when a user tries to register on our website, then we ask them for the registration password, which we turn into a hash using our hash function, and then we store that hash on our database. Now, at a later point, when the user tries to log in and they type in their password, then we again hash that password that they typed in to produce a hash, and then we compare it against the hash that we have stored in our database. And if those two hashes match, then that must mean that the login password is the same as the registration password as well. And at no point in this process do we have to store their password in plain text, or are we able to reverse the process to figure out their original password. The only person who knows their password is the user themselves. Now, previously we saw that by using the Enigma machine, as long as we knew what the settings were for the Enigma machine, which is basically the encryption key, right? As long as we knew what that was, then I can decode it by setting it to the same encryption key. And we end up being able to retrieve the original text. Now, however, if I was to go and change this to a hash function instead, then you can see that when we try to decode this using the same hash function, MD5, we get the error that decoding step is not defined for hash function because you can't really go back. That's the whole point of the hash function. And this is what will make our authentication more secure. All right, guys, so now that we've covered creating user passwords, encrypting our database, as well as hashing passwords, we've kind of reached a level of security that most websites are at. Now, there's a lot more security that we're going to learn about a little bit later on. But you're actually at a point where you already know quite a lot about authentication and keeping user passwords secure, and definitely a lot more than a lot of people who actually run websites. And I know that some of you guys are keen to get a job, and if that is you, then I want you to go onto a website called plaintextoffenders.com. I'll link to it in the course resources. But here, what you'll find is emails that come from various companies where the user is requested to reset their password, and they're sending the user a plain text version of their password. Now, at this point, we know to be able to even get the user's password in plain text, it means that they're doing some horrible things with securing the passwords. Either it's encrypted and there's an encryption key somewhere that they're storing, or it's simply just stored on their database as plain text, which is the worst possible type of security. So given that you already know a lot better than the people who run getlinuxjobs.com or worldsim.com or Telecom Egypt, then you could actually just email these people and tell them that I'm a web developer and I know about authentication and securing users' passwords. You obviously seem like you might need some help. Would you like me to work for you? I recommend giving that a go if you're keen on getting a job. If you're not looking for a job, then have a look at these websites. And if you're signed up to any of them, be sure to delete your account because it's definitely not secure. And this is why a lot of companies and a lot of websites get hacked, because they don't continue beyond this point. So that means it's a really good time to talk to you about how passwords are hacked. So a sort of hacking passwords 101 class, if you will. Now, most of the time I use my programming powers for good, but in this case, I want to talk to you about how passwords might be hacked so that once we understand how the other side approaches this problem, then we can learn more about security and make our website safer for users. And by the way, I have no idea why hackers are always portrayed in a balaclava. It's not like they're going to burgle anybody. I mean, especially this guy. He must be incredibly warm sitting next to all these computers, wearing so much clothing on his face. But I digress. So, as a company, this is probably one of the things that you least look forward to. The day when you wake up and you get a call and you've been hacked. And this has happened really recently to a lot of big companies like Adobe Creative Cloud got hacked in 2013, LinkedIn got hacked in 2012, and there's loads of accounts where their passwords get leaked. Lots of unhappy users who reuse their passwords and are feeling extremely vulnerable. And you can see that even to this day, people can purchase these hacked accounts where people might not have realized that their LinkedIn email and their passwords are linked, and people are potentially buying that data up and using it to hack into their PayPal accounts or other similar payment portals. So even if you don't learn anything from this lesson, I recommend just going to this website. I'll link to it in the course resources just for educational purposes, but put in your email address and make sure that if you do have any passwords that show up, change all the places where you use that password. But why is it that all of these big companies are getting hacked and leaking their users' passwords? Are they not at least encrypting or hashing their passwords? Well, they are. But consider this. So you're a hacker and you've managed to get into the LinkedIn user database. And just for simplicity's sake, let's say it looks like this. You've got a username and you've got a hash. And thankfully, they didn't store their users' passwords in plain text, so you can't access their passwords straight away. However, if you look at this table a little bit more closely, you'll realize that 3 of the hashes are completely identical. Now, why might that be? Well, remember that the same password always turns into the same hash, no matter how often you try it. And that's a core part of the hash function that we rely on in order to validate our users as well. So that means a hacker would look at this table and realize that Angela, Tony, and Emily all have the same password. And what they can do is they can start to construct what we call a hash table. So you would take some of the most commonly used passwords and you would use the same hash function to create the hash value for each of those. And these are some of the most common passwords that people love to use. 123456, QWERTY, password 111111. And so you generate this hash table, and then all you have to do is just look up the hash of the user and compare it against the hash you have in your table. So you search by the hash value and you land upon the password, which is QWERTY. So now you figured out that 3 out of 4 users in this table all have the same password, and it's QWERTY. So what if they didn't use one of the most common passwords and instead they use something else, say their date of birth or their pet's name? Well, let's see how we would make a hash table if we were a hacker. You would probably start with all the words from a dictionary, and this is where the term dictionary attack comes from. You create hashes from all the possible words in a dictionary, and that will only be about 150,000 hashes that you would need to create. And then you add to that hash table all the numbers from a telephone book and all the combinations of characters up to 6 places. And then you add all of these together and you end up with something close to 19.8 billion combinations, which admittedly sounds like a large number, right? How long would it take your computer to calculate that many hashes? So what do? Well, let's go shopping. Let's go and buy some of the latest GPUs or graphics cards, which are capable of parallel processing and therefore are particularly suited to not only Bitcoin mining, but also generating hashes. With one of the latest GPUs, you can calculate about 20 billion MD5 caches per second. So that means with our hash table of 19.8 billion combinations, it'll only take one of these GPUs 0.9 seconds, which is nothing. It's not a lot of time to invest in order to hash so many people's passwords. And to make it even worse, large hash tables have been built for the most common passwords. So because we've had so much data from previous hacks, such as the Adobe one or the LinkedIn one or TalkTalk or Equifax, we know what the most common passwords are that people use. And every year, companies like Splash Data will compile what are the most common passwords, say the top 25. And this is where all of those values that went into our table came from. But you can actually go one step further. There are pre-built hash tables that people have created for the top 10,000 most common passwords. And you can see that MD5 is one of the quickest hashes to calculate. And this is why it's very, very common to find MD5 hash tables. And you can even use Google as a basic hash table. You can paste in the hash that you found from the hacked database. You perform a simple Google search and you come up with the original password. Now, if at this point you're extremely scared and you're wondering, well, what exactly can you do about this? Well, consider that in our user table, there was one hash that was extremely difficult to find, and it didn't match up with any of the hashes in this little simple hash table we built. So what if we put that into Google to search on a larger scale and see if it matches any of the hashes in the hash tables that people have generated? And it doesn't match anything. And the reason is because when John created his password, he had a very, very strong password with uppercase letters, lowercase letters, numbers, symbols, but most importantly, a long password. When you think about hashing as a mathematical formula, you'll realize that as the number of characters of your password increases, the computation time that it takes to crack it increases exponentially. So it doesn't matter if your account on LinkedIn or Adobe Creative Cloud or Ashley Madsen was cracked, as long as you had a strong password, they wouldn't be able to work it out from a hash table. So as an example, there's a website called Password Checker. And you can put in your password and it'll tell you not only the strength, but also how long it'll take various types of machines to be able to crack that password. So let's say that I create a 6-character password composed of a random set of characters, right? 1, 2, 3, 4, 5, 6. And you can see that even for a standard desktop PC, it only takes about 3 seconds to perform a brute force attack to crack that password. But let's see what happens if I add another 6 more characters. 1, 2, 3, 4, 5, 6. Now it takes 31 years for a standard desktop PC to be able to crack it. And even a fast GPU takes 2 years to crack my password. So even though all of the websites encourage you to add a capital letter, a lowercase letter, some numbers, and some random characters, if you only have 6 characters in your password, so a short password, it still doesn't take very long to crack. So the most important thing of creating a strong password that is almost uncrackable is just to increase the number of characters. And also, to prevent yourself from being a victim of a dictionary attack, just make sure that you don't use a dictionary word or a place name or something that is in a directory somewhere, like a telephone number. Alright, so at least after this lesson, you'll know how to keep yourself more secure. But in the next lesson, we're going to address these vulnerabilities that occur because of weak hashing algorithms, and we're going to learn how we can combat hackers who try to attack our database using a dictionary attack or by creating a hash table. So for all of that and more, I'll see you on the next lesson. But as a quick bonus, if you ever want to trick your friends into thinking that you're some sort of a hacker, at least according to Hollywood, I recommend checking out a website called hackertyper.net, where you can just mash the keyboard and you end up with something that looks extremely realistic. But word of warning, try not to do this on an airplane or in a government building unless you want to actually get investigated. All right, so now that we've seen what some of the vulnerabilities might be for hashed passwords, it's time to level up and learn about a way that we can prevent these types of dictionary attacks or hash table cracks. And in order to do that, we have to learn about salting. Now, what exactly is salting? Well, we already know what hashing is. It's when we take a password, we run it through a hash function, and we end up with a hash that we store on our database. And as we saw in the last lesson, passwords that are generated by humans are extremely insecure. They tend to be very short, and they tend to be dictionary words that are extremely easy to look up and create a hash table for. Now, salting takes the hashing a little bit further. In addition to the password, we also generate a random set of characters. And those characters, along with the user's password, gets combined and then put through the hash function. So the resulting hash is created from both the password as well as that random unique salt. So that means no matter how simple the password of the user is, adding that salt increases its complexity, increases the number of characters, and we make our user database a lot more secure. So consider the previous problem that we saw in the last lesson, where we covered Hacking 101. Now we know that 3 of our users have the same password, and we figured that out because they all had the same hash. Now, on the other hand, if we had generated a random set of characters, which is the salt, and combined the password with the salt in order to generate the hash, then they won't have the same hash in our user database. So let's try and generate Emily's hash from her password. So we know that her password is QWERTY, and we generate a random salt. So then let's go ahead and put in her password, QWERTY, and then we append at the end that random salt that we generated, and we end up with a hash. Now, this hash, however, is not the same as Tony's hash or Angela's hash because the salt is different each time. Now, the salt is something that the user doesn't have to remember, and instead it's stored in the database along with the hash. So that means when the user types in their password when they try to log in, you combine their password with the salt, and if you generate the same hash, then they must have had the same password. It's kind of clever, isn't it? And on our database, of course, we wouldn't be storing their passwords, but only the salt and the hash. Now consider our previous statistics. You can generate about 20 billion MD5 hashes per second. So even if we added a salt and we made it harder to generate a hash table, with some of the latest GPUs, you can still probably generate a hash table with all salt combinations relatively quickly. So what else can we do to increase the security? Well, we can use something other than MD5, right? Another hashing algorithm that's valued because it's incredibly slow. And this is where bcrypt comes in. This is one of the industry standard hashing algorithms that developers use to keep their users' passwords safe. Because while you can calculate 20 billion MD5 hashes per second, even the latest and the greatest GPUs in 2019 can still calculate only about 17,000 bcrypt hashes per second, which makes it dramatically harder for a hacker to generate those pre-compiled hash tables. And a salted hash table, instead of taking something like 3 seconds if it was hashed with MD5, if it was hashed using bcrypt, it would take you something like 8 months, which is not really worth a hacker's while. They'll probably go and search out a company that has less security enabled. And to make our passwords even more secure when we're using bcrypt, it has a concept of what's called salt rounds. How many rounds you're going to salt your password with. And obviously, the more rounds you do, the saltier your password. And also, the more secure it is from hackers. So what exactly are salt rounds? Well, let's say that our original user password was QWERTY, and we generate a random set of characters as the salt. So now we have QWERTY and a random set of salt. We pass it through our hash function, bcrypt, and we end up with a hash. Now, that's one round of salting. If we wanted to have 2 rounds of salting, then we take the hash that was generated in round 1 and we add the same salt from before. And now we run it through bcrypt, the hash function, again, and we end up with a different hash. And the number of times you do this is the number of salt rounds. Now, the reason why this is genius is because as computers get faster, remember that Moore's law says that every year the number of transistors in a computer chip almost doubles and the cost of that faster computer halves. So every year you can get more computing power for less money. And this is where salt rounds comes in. When you're hashing your passwords using bcrypt, you can set the number of rounds you want to salt your password. So that means maybe this year in 2019, you salted 10 rounds, but maybe next year you can increase that number to 12. And for every increase in that number, the amount of time that it takes to hash your password doubles. And so that means you don't have to change your hashing algorithm or update your code other than simply changing one number to keep up with the times. So just to review, coming back to that user database, we'll have each user's username stored, we'll have their randomly generated salt stored, and then we'll store their hash after a set number of salting rounds. And when it comes to checking their password when they log in, we'll take the password that they put in, combine it with the salt that's stored in the database, and run it through the same number of salting rounds until we end up with the final hash. And we compare that hash against the one that's stored in the database to see if they've entered the correct password. So let's give that a go in real life and implement salting rounds into our website's authentication.